As far as I know, they haven't said that there's map testing tomorrow, so I think they're gonna try to get through map testing today.
Oh, like
And
the whole
then-
thing, like,
Well, just the reading
oh,
portion,
okay.
because they want to get that up and running, and then hopefully I can hear something confirming that tomorrow is a regular school day.
It could be just like a math portion too, they're trying to finish.
Right, but we don't know, hoping that it'll be sometime.
Okay.
All right, so we're going to start our next unit. Obviously, not going to be on the test, but hopefully you guys are able to spend some time beginning to review for your tests. Hopefully yesterday you started your test review. Tonight you get to do some review as well. I will have a morning help session tomorrow at 7:15, going over test review 3. I know there's some students who can't make it tomorrow. I will have a short help session this afternoon, 3:30 to 4. If you want to come by for that, and I'll record that as well. So if you have just any small questions that you want to ask this afternoon, I'll be available. But tomorrow is the one where I'm going to have a dedicated time for that. Yeah.
Do you have a calendar numbers?
Not yet.
Okay.
We're just going to do, I'll have the September calendar for you after the break. Okay, so 2.1 and 2.2 are I'm kind of merging them together. Really the focus is on 2.2, but I'm putting them to the same section. So if you see 2.1 or 2.2, just know that it's referring to the same. And in the homework assignments, this homework will be due on Friday. Okay. Now, let me talk about your packet for a second. So I try to make things hopefully a little bit easier to find. I try to put everything into one packet rather than splitting between 2 packets with your exercise problems and your notes. So we're going to start with notes on page 1. But then after that, we have some practice worksheets, and then your homework problems are directly inside in your packet in chronological order, the way that we're going to do it. So I have the exercise problems starting here on page 7, and then the AP practice problems on page 8. And then I go into the 2.2. Well, 2.1 and 2.2 are kind of the same, so I put them all next to each other. And then you see the notes for 2.3. So hopefully things are easier to find. The way that the order that we're going to be working through the problems is going to be the way the packet is organized for the most part. I think sometimes things may be, for the most part. And if it's not quite in order, it should be really close, like just next to each other. Okay. So I will make a reminder about this tomorrow in the remind, but just to let you know that starting with this unit, I want to see your work on a separate sheet. I feel like, if you do work in the margins of the exercise, there's not enough space for me to see your work. So I want you to show your work on a separate sheet. And if you're if I have dedicated pages for you for the AP practice problems. Okay, so I want you to do your work on the page that I provide for you in the packet. But if this is exercise pages, I want you to put this on a separate sheet. Okay, and also I'll send a reminder about this as well, that if you are just going through this and you're just circling through the answers and you're not showing your work, I'm going to ask you to do it again if you want credit, okay? Because I can't tell if you're just spending 5 seconds circling the answers, right? I want to see that you're spending time attempting the problems and trying to do the work. And I have all the solutions, everything worked out, detailed on the website. So if you're stuck on something, use that to see if you can help get going, rather than just putting a question mark saying that you don't know how to do it. At least show me that you attempted to look at the problem solutions and try to figure out, right? If you don't understand, that's fine, but I want you to at least attempt it rather than just put a question mark next to it. Okay, so I'll send out a reminder about that tomorrow after the test in a remind so that you know what to expect on upcoming homework if you want to receive credit. Okay. Okay. All right. So we're going to transition from limits into what we call derivatives. And so after we make that handoff, we're not going to see a whole lot of limits anymore. Limit is more like as a bridge between algebra and calculus. But then once we cross that bridge, we're going to leave it for the most part behind, and we're going to have a much, the foundational piece that we're going to use is going to start this unit. Okay, so we start with limits because it does provide that bridge, but then we're not going to see it for a while as far as limits go. But we are going to see it initially to provide that bridge. So let's go to page 1 here. I know I have a bit of a short period, so if I don't get through everything, I may use some of Friday to do it. All right, so let me start off with a question here. If I asked you for slope of a line, what information would you need, and how would you go about finding it? Okay, so what information would you need if I want to ask you a slope of a line? What information would you gather to get to the slope of a line?
Yeah.
2 points, right? 2 points, because you can, if I gave you order pairs, you can do y2 minus y1 over x2 minus x1, or you can do rise over run. You can just count. And then let's say the slope is 3. Is that slope going to be the same no matter where I am on this line?
Yes.
Yes, right. Same slope, right? It's constant, never changes. Okay. So once you find the slope of the line, then I'll ask you what that slope is, and you just say 3, and that's the end of the problem, right? But what if I asked you, what is the slope of a curve? How would you respond if I asked you, what is the slope of this curve?
What part of the curve?
Good, right? What part of the curve, right? Because it's always doing what?
Always changing.
It's always changing, right? So that's the difficulty of something that we have here, right? It's always changing, so it really depends on a point on the curve. So what if I ask you, what is the exact slope at this point? I mean,
You have to look at like you only look at that certain interval.
okay. But in order for me to find the slope, I need what?
Tangent line?
Okay, I need 2 points, but here, a tangent line is only hitting 1 point, right? So maybe you can give me a really good approximation if I pick 2 points really close, but how can I get to the slope of that exact graph, that point on the graph? So that's where, yeah.
Well, you can include like that same approximation to point on the bottom curve. Like,
Oh, you mean down here?
yeah, like the
There's no guarantee, right?
Okay.
There's that, I mean, maybe if there's symmetry, we can find that. But the idea is that we can find a pretty good approximation for the slope, but I'm asking for the exact slope, and that requires something a bit more than just algebra. Okay, so that's the goal that we're trying to reach today. Can we find, how can we work with the slope formula so that we can turn it into something that only requires 1 point? Okay, all right, so this is really the big idea behind calculus. Okay, so now that you have that picture in mind, okay, let's say this is the curve that we're working with. Okay, the curve is f of x, and the goal is, let's say we want to find the slope of this. Sorry. Yeah, let's say the goal is to find the slope of this tangent line. But the issue is that this tangent line is only touching 1 point of the curve, and we just talked about how, well, if I want to find the slope, I need 2 points, right? I don't know how to find the slope if I just have 1 point. But maybe we can start off with an approximation. Right? So I'm going to use this secant line as an approximation. So the difference between tangent line and secant line is tangent line is a line that skims the surface of the graph at 1 point, but a secant line is going to touch the graph how many places? 2, yeah. So, but we can find the slope of a secant line because if I give you order pairs of P and Q, you just do rise over run and you'll find the slope, right? Now, if I have the secant line approximation, is this a really good approximation or is it just an okay approximation of the slope of this tangent line?
So, okay,
It's just okay, right? I mean, they're both positive, but it's not great, right? This is not very steep and this is a lot steeper. So the question is, can I create a secant line slope that is a better approximation that's closer to what this tangent line is? Or is there anything I can do with these 2 points to help me get a better approximation to getting closer towards this tangent line?
finding a derivative.
Okay, that's what we're going to be talking about. But in terms of slope, though, what if I were to move that point Q? What happens if I move the point Q closer towards point P? What's going to happen to that secant line approximation?
It's gonna change.
Okay, for the better or for the worse?
Better, or better.
For the better. Why?
It's a closer estimate.
Get closer, right? Closer. So if you look at this graph here, this approximation, this picture just shows. Let's say we start off with Q1. Okay, we use P the same way, but let's say we do Q1 and P, and then Q2 and P, and then Q3 and P. You see that as we get closer towards our point of tangency, our secant lines will become better and better. Okay, you guys see that? So obviously, if I pick a point really, really close to point P, I'm going to get a really good approximation. Okay, so what if we can do this? Okay, what if we can somehow use limits to decrease the distance between P and Q, where that distance becomes so small that the distance between them turns into 0. Okay, so that's the idea, is that we're going to not only work with a really good approximation, we're going to turn that approximation into an exact value, into an exact slope, where something that initially requires 2 points, we're going to turn it into a thing where I can merge those 2 points into one, and I can use that to allow me to just get the slope requiring 1 point. Okay, so that's what limits is going to do for us. Limits is going to allow us to start with 2 points, but then decrease that distance between 2 points until that distance between them is 0, and it just ends up being just 1 point. Okay, so we use limits to decrease distance between P and Q until it is 0. And this process will improve the approximation of the secant line until the value becomes the exact slope of the tangent line. Okay. Right. Does that concept make sense? Right. So what you're going to see next is going to feel a little messy because we want to use variables a lot. Variables allow us to move things, right? So if I set 2 points in stone, it's hard for me to move it because those are just, if it's like a 2 and a 4, I can't move it. But if it's like an X and an H, I can start moving things. So it's going to look a little messy initially, but I just want you to think all I'm doing is I'm just going to take the slope between 2 points and I'm going to use limits to help me move those points closer. Okay. All right, so we're going to do this down here. Okay. I'm going to assign some order pairs for P and Q. Okay, but I'm going to use a lot of variables here. So let's say point P is some X value away from the origin. Okay, I don't want to give it a number. I just want to call it X. So if I plug X into the function, that will give me the Y value, but my Y value will remain a function notation. So for point P, I'm going to call this order pair X, comma, f of X. Right. I mean, we could say 2, 4 or 3, 5, but we want to have the flexibility. So I'm leaving them as variables. So that makes sense. F of X represents the Y value at this point that I'm specifying. Yeah.
Well, F of X is like a label for the line.
F of X represents the Y value of the curve. Right. F of X means Y value. So for instance, if I have F of X equals 2x plus 3, isn't that the same thing as Y is equal to 2x plus 3? So F of X represents the Y value of the graph. So I'll make sure that we are good with that, right? That f of x means the y value. Okay. Obviously, the y value is constantly changing, but at this particular point, it is a singular value. Now, point Q, let's say point Q is some distance away. So I'm going to call the distance between x and the x value of point Q. We're going to call it some h distance away. So maybe it's 3 units away, maybe it's 4 units away, but I'm just going to call it h. So what can I assign this to be then if this is x and this is h? Good, x plus h. Just some x plus h distance away. If this is 2 and this is 1, then it'll be 2 plus 1. If this is 4 and this is 5, it'll be 4 plus 5. But I'm leaving them as variables because I want the flexibility to change and move it. So if this is x plus h, if this is the x value of my point Q, what do you think will represent the y value of my point Q? Good. F of x plus h. I'm just inserting my x value, quote unquote x value, into the function. And that is in function notation. Okay, so we have 2 order pairs. They're obviously not set in stone. We're just letting them float at those notations. Okay, are we good with that? Okay, so let's say I ask you to find the slope between those 2 points. Okay, so let me just assign it x1, y1, and this is x2, y2. What would the slope look like if I want you to use those notations? Oh, yeah, good. Right. So my slope is simply y2 minus y1 over x2 minus x1. Okay. Like Julian said, we're just going to take these function notations and put it into our slope formula. Okay, so hopefully you guys are still with me. It feels messy because there's all these messy variables there, but we're just doing slope, right? We're just dealing with slope, and we're leaving those variables with the flexibility to move and change. Yeah.
You're mentioning it as values for those coordinates.
Well, we're going to work towards a formula, and that formula will be used for future problems. But right now we are giving that flexibility where this can work for any points that I start with on the graph. Okay. Now, can I clean this up any further? Is there any like terms I can combine within this? Yeah, the x minus x, that can go away. I can't do anything with this, right? These are not like terms. So there's only an h left over at the bottom. So are we good with thinking of this as some variation of slope between 2 points, as abstract as it looks? Okay, you guys good so far? Now, what if, okay, so let's say these represent the slope between P and Q, okay? But then what if I am able to put this notation in front? So the notation here is limit as h approaches 0. So that means I'm going to take that distance between x and x plus h, and I'm going to start shrinking it. Okay? And if I start shrinking it, that means this point Q is going to start moving towards point P. But what if I can move it so close so that the distance between point P and Q virtually goes to 0? Okay. And so that leads us to our what we call a limit definition of a derivative, where all of a sudden I started off with 2 points, but I merge it into just relying on 1 point. So this is, you can consider this a more robust version of the slope formula. The slope formula has to have 2 points. But here, we start with 2 points, but we're merging it into 1. And if we do that, we can arrive at not just an approximation, but the exact slope of any point of a point on the curve. Okay. So let me start talking about some notations here. f prime of x, this notation with that apostrophe, this is the notation for the derivative of a function. And derivative is simply a fancy word for slope. Okay? It represents the slope or steepness of a curve at a single point. Okay? We talked about how if I, right now with algebra, if I ask you for the slope of a point on a curve, the best you can do is find points really close to it and find the slope, but it's not going to be exact. I mean, you can get a really good approximation, but you're not going to be able to get an exact. But here, with this process, we can get down to the exact steepness of a point on the curve. Okay, so this derivative function is a slope finding formula for the curved graph where the slope of the curve is ever changing. Okay, so back to this question. If I ask you what the slope of this curve is, you're going to say, well, it depends, right? But what we can do is we can create a formula that represents the slope of this curve at any point, where if I plug in an x value here, 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 or here into some formula, that formula will tell me the exact slope at any single point that I want to ask it. Okay. Just like how a function can tell me any y value that I ask, as long as I give it an x. But the derivative function now is going to tell us the steepness of every point on this curve without us having to go through, a messy process of finding slope every time for every point. Okay, so that's where we're leading towards. Okay, any questions so far?
So this is how you find out the exact values.
This is how we're able to get to the exact slope of a point on a curve.
Didn't you say like it's gonna so when you make the limit like equal to 0, right? You limit h over 0. You said it's gonna be as close to 0 as possible, right?
Mhm.
So then that means still like kind of like an approximation, even though it's not exactly.
Well, it starts off as an approximation, but if we do limit as h approaches 0, that eventually will reach 0. Okay, all right, it'll eventually reach 0. Okay, it's just like if I have a point on the curve and there's a hole here, right? If I ask you what the limit is as x approaches c, you would say that hole there, even though it never technically reaches that hole, it is the destination. So that is the limit, right? Okay, so let's look at the next page and let's see if we can do an example problem here. Now, there's also this alternate definition of a derivative. We'll get to that later. We're going to focus our attention on this general definition of a derivative. Okay, so let's look at this curve here. Okay, this curve is y equals x squared. That's something that we all recognize, right? It's a parabola that is centered at 0, 0. What we're going to do is we're going to find a slope formula for this curve. Okay, we're going to find a derivative function for this curve using this limit definition. Okay, so let me walk you through this process here. This is where this x plus h is going to come in handy. Remember, we did this process in chapter P, and now it's going to come back in a way that hopefully we can kind of understand that algebra process a little bit better. So the whole idea is that we're going to try to get this function into this numerator and then work it out for this particular example. So a slope formula is going to be different for every curve, right? So every curve is going to have its own dedicated slope formula, right? Because every curve is changing in a different way. So you have to make sure that every function has its own uniquely built slope formula. Okay, so we're going to build a unique slope formula just for this curve, okay, and just for this curve alone. So we have to find some substitutions, right? F of x is x squared, so that's easy. That's just easy replacement. But the hard part is, how do we find a replacement for that f of x plus h? So I'm going to help build it piece by piece. So first thing I want you to do is, okay, here's my function. But if I want to figure out where that x plus h goes, I'm going to create a reserved spot for that x plus h. So we talked about before how if we want to put anything into the argument, we want to remove the x and have a space reserved for the new argument. Okay. So now I've removed the x. In place of the x, I have an open parentheses. And guess what I can put inside that parentheses now? This will be the x plus h. Okay. Okay, so here's my derivative function. I'm just going to put it piece by piece in here. Okay, what can I replace the f of x plus h with? Okay, x plus h squared. Minus x squared. Okay. So we're getting the numerator out of function notation so that we can actually begin playing with it.
Why do you get out of function notation again? And you bring it to that?
Because if we live in a function notation, it's hard for us to add and subtract and combine it because these aren't like terms. Right, but if I get it out of function notation, I can begin to combine some like terms together and get it right and work with it.
And it'll change based on like what the function is.
Yep. So we'll get there. But yes, it will turn into a formula that will adapt to the changing slope of this curve. All right. So this is a limit problem approaching 0. So before we go any further, right, this is approaching a real number. So if we want to evaluate a limit algebraically, we just plug in 0. So replace 0 in for h. And what do you notice? 0 over 0, which means that there's a what? There's a hole. We're going to remove that hole. And so we're going to go through our limit process. So even though we're in a new unit, we're kind of reviewing our methods of limits, right? We're going to approach a real number. Yes.
You got rid of the x plus h squared and like it became x squared.
Well, the f of x plus h is equal to x plus h squared, so that goes here. And the f of x is equal to x squared, so I made a replacement with that over here. So I made two substitutions, right? This is equal to this, and this is equal to this.
What's the bet? Yeah, like what's that for?
Right. So I have to figure out what f of x plus h is for this function. So basically, this is my new argument that I'm inserting into the x of my function. So the way that we had it before was, if you want to put anything inside your function, the first thing you do is you go ahead and put some reserve spaces around the x so that we're removing the x, and in place of it, we're putting the x plus h. Does that make sense? All right, so anytime I want to do x plus h, I have to put it into the reserved spots of my function. Right? So we always want to do this step. If you always put parentheses around where the x was, then you're never going to put the x plus h in the wrong place because there's only one place you can put it inside the parentheses. All right, so now we got to clean this up, right? We got to FOIL all this out. We got to find the hole. We got to remove the hole and then reevaluate. Okay, so we got to FOIL this out. So a lot of like terms can combine and go away here. X squared can go away. We can combine x plus xh plus xh. That combines to be what? 2xh. Okay. Okay. What can we do in the numerator here? And factor out a what? H. Can we find the hole and remove it? The h, right? So remove the h. And then what's our final step? Yep, put in the 0 in for h. Yep. So my f prime it's just 2x plus 0, which is 2x. So if you were asked now, what is the slope of this curve? You can't give a single number because it's always ever changing. But what you can say is the slope of this curve is 2x because it is changing according to this pattern. So that means if I want to find the slope at this point, I'll just plug in x value into the derivative function, and in return, it'll tell you the steepness at this singular point on the curve.
Why do you look at apostrophe in like that?
Oh, right. So that notation, that apostrophe, represents a derivative function. So we call that f prime of x. So f prime of x is the notation for the derivative function. So f of x is the original function. F prime is what we call this derivative function, which describes the rate of change or the slope of the original curve. Okay, so I want to convince you that this actually is the slope formula for this curve. Okay, so let me just ask you this here. What do you expect the slope to be at this point on the curve? 0, right? So let's see if it actually works out. So if I plug 0 into my derivative function, I should get a 0. And I do, right? 2 times 0 is equal to 0. Okay. So let's say I pick a point over here. If I plug in 1 or any point here, what slope would you expect here? Some positive or negative slope? Some positive slope. What if I pick a point that's further out, like a 4 or 5? Will it get steeper? Yes, right. So let's say I plugged in 4 into the derivative. F prime of 4, 2 times 4 is what? 8. So it's a pretty steep slope, and it's just going to keep getting steeper, like what you would expect. Okay, let's make sure we can convince ourselves on the negative side. Here, all these slopes are what? Negative. So any x value I plug in, I should get a negative slope in return. So if I plug in -3 into this derivative function, 2 times -3 is -6. So it's very adaptable, right? You know, we can find information about this curve without having to do just, approximation between slope. Now we have something that is much more efficient. Now we're going through this limit definition so that we can see that connection between limits and slope. But then after this section, we have a much more efficient way of getting to the derivative function. Yes.
Like at the top where it says f of x at x equals 1, would you just like find the slope of it?
That's right. Yeah. So right. So now let's see if we can answer this question here. This question is asking, write the equation of the tangent line to the function at x equals 1, and we're going to put it into point slope form. So you see this this little line that I drew? That's what question B is asking. It's asking for, can I create the equation of this tangent line? And if I want to create the equation of a tangent line, I need 2 pieces of information. I need the order pair, I need the slope. Because once I get the order pair and slope, I can put it into point slope form, and that is an acceptable form for AP exams. Okay? There's no need to do slope intercept form. Slope intercept form is fine, but point slope form is more efficient, and there's less room for mistakes. So I need to find, in order to find my equation of a line, I need to find an order pair, and I need to find the slope. So I know my x value is at 1. How can I find the y value at that point? Good. Good. So f of x will give you the location, the y value. F prime will give you the slope. So your function and your derivative, they both talk about the same graph, but they're giving you different pieces of information back. Okay, so that's really the biggest idea of this semester. If you can understand that concept, that will carry us all the way through. Yeah, so the function, the original function will give you, here, I put it down here. F of x is a height finding formula. It finds the y value of the graph at any point, but f prime is a slope finding formula. It will find you the slope or the rate of change or the steepness of any point on that curve.
That's like the most important concept you said.
Yeah, this concept is going to carry us through all the way through first semester. Okay, so back to our problem at hand. We want to find the order pair and slope. You said to find the order pair, we're going to plug 1 into the function. So I'm going to find f of 1. F of 1 is 1 squared. So that's just order pair of 1, 1. If I want to find the slope gets inserted into the derivative function. So f prime of 1 is equal to what? 2 times 1, which is 2. Okay, so we have our point, we have our slope, and now we can put it into point slope form. And again, what we're creating is we're creating the equation of this tangent line that I highlighted in red. Okay, so y minus y1 is equal to m times x minus x1.
The coordinate for the limit is like 1/1.
I'm sorry?
So the coordinate for the limit is like 1, 1, 1, 1.
The coordinate for the point of the graph is 1, 1.
Oh,
Right. Yeah. We use the limit notation to get to the derivative, but then once we get to the derivative function, we drop that limit notation. It's not part of our answer anymore. Okay. So can we do part C? Can we try that on our own here? It says write the equation of the tangent line of the function x equals -5. So imagine this is -5 here. How would you write the equation of this line here? All right, so find the order pair at this point, find the slope at that point, and just like before, you're going to put it into point slope form. Still doing the same graph. We're still using the same function. We're still using the same slope formula. So we're just creating an equation of a tangent line that is in a different spot. Okay. Again, your f of x is going to return you the y value. The f prime is going to return you the slope. Okay, let's check our answers. So if I plug -5 into the function, I'm going to get a y value of 25. If I plug -5 into the derivative, I'm going to get -10. That makes sense, right? Because you expect the steepness at this point to be pretty steep in the negative direction. So -10, and the order pair is -5, 25. So you have your order pair, you have your slope, point slope form, and you can leave it in this form when you write the equation of a line. So this entire semester, we're just going to find more and more ways to find derivatives for more and more complex functions. But the idea is we have our function, we have our derivative, the derivative gets you the slope, the function gives you the y value. If you can understand that concept, it's going to be the same thing over and over again. Okay, that's the big picture. That's the big picture. Okay, so I think the bell is like going to ring in like 5 minutes. So you guys can come get your phones. Tonight, just study for your tests. Look over your test review. I'll have a short help session this afternoon, but I'll have a full one tomorrow starting at 7:15. I'll record both of them and I'll send you a Teams link tomorrow morning. Thank you.
if you're at something. Oh yeah, going to that Bills game. That's. I'm looking forward to that day. It's like, oh, we got it. Are you watching Hard Knocks? What is this? 2040?
I got a copy.
There you go.